maybe before I start talking about math, few acknowledgements. First of all, if we could maybe thank John for this wonderful local organizing. I'm always really impressed by the consistent high standards of hosting. So thanks, John.
Thank you.
And, the second,
And it was great. I got that on tape. So
the second piece of acknowledgement is to the NSF who did fund this CBMS program, to the people who actually applied for the grant. So that's the other organizers. So John and Nair, Lisa Trainer, Lenny Ing, and Valenta Soon as well. And then also special thanks to James Hughes, who gave one of the presentations, Hong Hao Gao, the other one, and then Wen Yuan Li and Ursula Capovilla, who also gave the research talks.
I wanted to add one person. So unfortunately, she's not here today, but Stephanie Cook is the one that essentially has made all the stuff behind the scenes, like all the food that appeared. She made that happen. So I would really like to have thanked her in person, but we can thank her in spirit.
Very important.
There you go.
I was trying to find a good way to summarize a description of what I'm going to be talking about. I don't know. I'm just going to be talking, okay? So everything that's been said so far, it is rigorous. I can point in the literature to papers. I can explain exactly how it works, so on and so forth. But I thought that I would also take the opportunity in this kind of last lecture to talk about things that are not immediate from the literature, things that maybe we can hint a proof or a strategy at, but it's not implemented, or things for which there's no proof that, you know, there they are. So yeah, the brief joke is none of what I'm going to say is in the literature. Some of it I know how to prove, and all of it is true. So okay, so let's start by just thinking about positive grades for a second. And so here's the first conjecture. C stands for conjecture. So the first conjecture in here is you take a Legendrian link that comes from either a rainbow closure of a positive braid or a -1 closure of a positive braid. Choose your favorite one. So you take this to be a Legendrian link. And then for this class of Legendrian links, add the double do not at the end, we have been discussing how sheaves, and you can also use floor theory, do give you a cluster structure. So let this be a Legendrian link. By the discussions in the lectures, we can consider that specific component of the derived stack of sort of perfect objects in the shift category. So then this space M, and remember this is just thought of as M1, lambda beta, let's point it. So recall from the lectures that this is effectively an affine variety. So right now I'm not doing anything out of the ordinary. This is a commutative algebra. So it's a commutative algebra. There's nothing else being said here. Commutative ring. And we discussed that this is clustered. But we're going to say something more than this is a cluster algebra. So that we know. So I'm going to write a little thing in orange that indicates that part of the statement we're okay with. Such that, and now the claim is that Lagrangian fillings, exact embedded Lagrangian fillings of lambda are exactly classified by the cluster tori we were discussing. So Lagrangian fillings, again, embedded exact Lagrangian fillings of lambda beta are in one-to-one bijection. And it's not just an arbitrary set theoretic bijection. We've discussed all of these, how Lagrangian filling L will give you a toric chart. It's exactly that chart that I'm thinking about. The cluster seats, so think of them as the cluster tori, cluster seats of that cluster structure. So some things are being said implicitly when I write these kind of things. So things will not be fundamentally wrong because they will be vague enough. But you know, because of that, maybe they're also fundamentally right. So one thing I'm saying, for instance, is I would expect these to be able to be named intrinsically symplectically. So I don't expect two different cluster structures on the same space. So maybe this cluster algebra is actually purely invariant symplectically. There's a unique one, and then it's satisfied that there's a one-to-one bijection. So comments are going to come in orange. So we know, okay, that every Lagrangian, every cluster seat contains at least one. So this map from left to right is bijective Lagrangian filling. And the way to argue is literally the theorem from the first lecture today, where you actually produce by hand Lagrangian filling, L compressing systems. You show that the equivalent potential is rigid, and so you can mutate forever. Okay. So really a very important part of the question, the main part of the question is, does PL uniquely recover that? So if you have two fillings for which both tori coincide, and think both tori with their cluster algebras imply L is Hamiltonian isotopic to L prime. That's the question. And I see that, and I'm happy to elaborate on that, but I see that as a generalization. So this is some generalized nearby conjecture for surfaces. So surfaces being the Lagrangian. So if you want to prove that, I have some suggestions on how to prove that in some cases, but I don't think you can prove these for arbitrary fillings without going through the nearby Lagrangian conjecture first. So I think maybe the first task is to just take a genus 2 surface and show that any exact Lagrangian embedded in that cotangent bundle must be Hamiltonian isotopic to the zero section. Does that make sense? And then you start adding disks with the L compressing system, and you're going to have variations on that. Thought about is a fair amount. I mostly come up with like one strategy, but any other strategy, including that one, it always goes through some sort of geometric analysis / PDE. I think something that could work would be starting with just algebraic lengths, for instance. So you just might say you tried for 2n torus lengths or something like that, or 2n torus not. We don't even know for the trefoil, right? So let's just start by those ones. And then you could imagine an argument that kind of goes like that. So you have the trefoil, which is the kind of Legendre in the end. You have a Lagrangian, but think of this picture as being some kind of hyperkähler rotation of something else. And then what you're trying to do is, well, you're trying to make that Lagrangian a J holomorphic. There's some choice of J that will make it. So with the hyperkähler rotated, you make it symplectic, and there's some choice of J holomorphic structure in there. And now the point is, in that cotangent bundle of the disk, you have this J almost complex structure that makes your surface J holomorphic. The zero section, you can also make it J holomorphic. And now the challenge is the projection onto the zero section J holomorphic or not? If the projection onto the zero section stays J holomorphic, by that J that exactly makes that surface J holomorphic, that would imply, because it's a J holomorphic map, that the image of this thing has to be exactly a 2-weave. So why? Suppose you have, this map is all relative to the boundary, right? So holomorphically on the boundary, you're going to have the standard J. And so you're going to have something that's standard J that will force whatever is inside to have 2 sheets. And because it's holomorphic, the real part of it is going to have codimension 2 similarities, which forces it to be a weave. And because it has 2 sheets fixed, that will fix it to be a 2-weave. So that becomes now a problem, kind of a PDE problem, which is sort of just not explored in the literature much, but it's, if I give you a smooth map or a J holomorphic map, a smooth map, maybe almost complex map, like formally so, can you deform it so that it becomes J holomorphic? And if you can do that, for instance, this kind of strategy would at least prove you that for 2n torus knots, you exactly have a Catalan number of fillings. So that's one kind of philosophy that one can try to take, but again, when I think about this, I don't know how to get away without at some point solving some kind of serious PDE problem, making certain map harmonic or making certain map J holomorphic. So if anybody has any suggestions, absolutely open. But I don't know a strategy not involving that. Does that make sense? Do you have any comment, Lenny, or you're okay? So as a quick comment, just kind of for kids, so a remark, it would imply that the torus links T to N have exactly a Catalan number of fillings. So a Catalan number, the same ones that you find wrote in her paper. This is exactly a Catalan number of fillings. Not, we know there's this many, but we don't know these are all. It would also imply, by the way, in all of that all the fillings are weaves. So that's kind of also one. For kicks, I think 3-4 would have exactly 8-3-3 fillings. So the trefoil and the what's called the E6 singularity, it would have some number like 4,000 something, and this would have 25,080 fillings. So the 35 torus not. But there's some numbers that the cluster algebra theory tells you this should be the answer. And we know we can build this many again with weaves. There's no example of a filling that we cannot do with weaves in all these examples. So, potentially we just imagine like all of them are going to come from weave, and that's why this kind of homomorphic thing might make sense. Okay. So that's the conjecture. The conjecture actually everything we're seeing right now, all the shift theory is actually detecting everything there is. There's nothing else. Does that make sense? Known for the unknot. Hopefully in the next month, an archive paper will show up saying this is also true for the Hoffling. Unknown for the trefoil. Say we don't know the answer is fine for the trefoil. Are we okay so far? Okay. So as numbers increase, the level of I don't know, dreaminess will increase. So C2. So now you say, okay, this was a whole discussion about positive braids. How much is this about Legendrians that come from positive braids, but actually general Legendrian? So C2 says, I think this has nothing to do with positive braids. I think it's a completely general phenomena. So now let lambda be any Legendrian thing. So lambda inside of P be any. It doesn't have to come from a braid. So yeah, Legendrian link. Then exactly the same conjecture. Then there exists a cluster algebra structure. So there exists a cluster algebra structure on the ring of regular functions of m lambda, which now we're going to briefly discuss, such that it classifies Lagrangian fillings. It seeks classify Lagrangian fillings. You want to think about augmentations, I would be saying something like the charts in the augmentation variety. So those are exactly the ones corresponding to fillings. So I'll elaborate more on this comment, but there's a C2 prime version, a C2.5 version of this conjecture in here. So this one is essentially telling you this should be true for anyone. Like doesn't matter, it comes from a positive operator. So this is a more interesting variant, which is I'm going to first write it in the GA setting, and then I'm going to write it in the shift setting. So the VGA setting would be given a Legendrian link. So again, let lambda the Legendrian. Then the VGA is not just any old VGA. It has this very particular kind of cluster structure on it. So let this be Legendrian. Then the VGA, the Legendrian contact VGA. The algebra in here, J, I'm going to denote this by A sub lambda, is A, and here come the two words, non-commutative. So I'm taking this really as a non-commutative setting, non-commutative cluster algebra. And one thing I want to emphasize is DG. So just to be clear, I'm saying cluster DG algebra. So let me state the same statement for sheaves. And then I'll tell you what on this is conjectural, or how you would start to think about these things. So sheaf version, C2 prime sheaf. Same setup as before. Let F, so this is a particular guy I'm going to be calling F lambda, be the co-representative of the microlocal stock. I'm assuming maybe that lambda is a link, sorry, is a not for now. Otherwise, you take microstocks in each component. Representatives of microlocal stock of lambda. Then the analog of the DGA, and you would expect this guy to be completely isomorphic to this guy, is the endomorphisms of this object. These sometimes, when you're drawing pictures, people are gonna think of these as being like that. So if you're Legendre or not, people are gonna say something like, well, you take this linking disk in here, you take this sheaf, which is K here and 0 outside, and then you do something. I mean, what you legally do is you think of this as a skyscraper, a microrogal skyscraper, and remember in one of the lectures I told you about the left adjoint, and there's some formula for it, there's a left can extension. The answer is you apply that left adjoint to this, and you have no idea what this looks like. It's kind of categorical nonsense, doing a lot of the heavy work. In Chris thesis, it was proven, which is essentially the left can extension formula, sort of realized geometrically, that this left adjoint is actually done by positive wrapping. So there's this notion of positively wrapping with a stop on the Legendre lambda. So you will positively wrap this, and I don't know how to depict this, but it's going to start to positively wrap in some kind of interesting way and do some interesting things and get very complicated all around. And whatever beast you end up having, the claim is, and that's what the left adjoint does, is that the sheaf that you ended up with will have singular support on the orange guy. Again, the issue is this red guy, this green guy has no singular support on the orange, so it's not in the category. But the statement is there's a way to hit it so that it will do some like crazy thing nobody knows about. That when I mean nobody, I literally mean nobody. Like I've asked, you know, I'm not going to say names because I'm on camera, but I've asked every expert in the field that have talked about this functor and proven amazing things about this functor. Nobody knows how to do this example for the term. And now 40 years and 4 hours each time. So really nice exercise, really nice thing if you really want to write a paper which is very geometric, is how does this look like? Just like literally the trefoil, this little guy in there, go and flow it in a way that it's partially stopped at lambda. And this is something that you could literally start with a computer just to get a sense, like solve the ODE of how it flows, get a sense, and you know, you're gonna get like funny things like when the disk is coming from this side, it will develop like a Radameister 1 move like that, and then it will kind of keep going and going and going. So ideally, you would like a paper kind of like Lenny's paper on computable DGA invariants, which is Legendre invariants, which is like just computationally, you prove through geometry that this is how it wraps, but then you say combinatorially, here's a set of moves of what you're going to do. Mind you, the resulting sheaf, whatever it is, should have endomorphisms that should be quasi-isomorphic to the DGA. So that maybe already makes you think that maybe using the rep cores in some smart way might be a way to wrap this. So that to me is an interesting project. It's not sort of far off conjecture. It's something like a down to earth. What does this generating sheaf look like? But once you have a sense of what this guy looks like, its endomorphisms is a same thing, a non-commutative cluster algebra. So, cluster algebra. Okay, let's take a couple of seconds to unpack what is being said. Okay, so the challenge up here is that we do not know that there exists a cluster algebra, even if this guy in here is really an affine variety. So suppose for a second that this guy is truly an affine variety. You have a nice affine variety. Then question, is it a cluster algebra? And the way you would prove it is, well, you could try to prove it is the way I've been doing it, which is find a Lagrangian filling, find an L-compressing system. Now it's typically not going to be spanning the homology, but it's going to be kind of partial, but you take maximal under inclusions, and then that is your candidate. And then you try to prove that the same thing, the regularity theorem of the meroidromies, the whole machinery does work through. Now, one good thing is that when you and I wrote a paper sort of explaining how to conceptually prove without any computations, I mean, any sort of algebraic computations, that the meroidromies are regular. So remember how what James did and everything, the initial proof that the meroidromies were regular, it involves some number of like ZIs and the polynomials and everything. After that, there was a proof that when Johan and I gave, which was much more conceptual. It was a geometric criterion for doing that. That criterion applies for any lambda. Okay, and it actually applies for any lambda and any Lagrangian filling in any Weinstein manifold. It's a kind of very general criterion that says if the meroidromy is being taken along a curve, which intersects every disk in the uncompressing system positively, then your warranty is going to be regular. So intuitively, the only contributions of poles come exactly for the negative crossings. And that is something that doesn't need lambda beta, doesn't need anything. It just needs the filling, the uncompressing system, that's it. So kind of in the spirit of Lisa's question yesterday, here the weak calculus is what allows you to, one, find a filling, but more importantly, a filling with an uncompressing system. So my sort of overall challenge or suggestion is, let's find a way to find uncompressing systems for general Lagrangians. Okay, finding fillings, I know it can be hard, but let's just say, suppose you have a filling. So you're given lambda and you're given a filling. How do we find good ways to find L-compressing systems? Say, for instance, we can do that for many max TV representatives of Lagrangian twist knots, but not like all of them. Like we can sort of, so, but you could imagine to start to develop theorems that says for all these families of knots, max TV, these or that, or pretzels or something like that, here's how you build L-compressing systems. And then what I'm saying is, once you have the L-compressing system, you might try to use my theorem with Wen Yuan in conjunction with my theorem with Hong Hao to just deduce that you have a cluster algebra number one, and actually any seed comes from a filling. So yeah, that would give me something. Yeah.
Do you happen to know what are the first few twist knots we don't know the answers for completely? The other, okay.
Like the M52 that has a Lagrangian filling,
right?
That I understand, but I don't understand the other.
I see. Okay.
So
you don't have to go too far.
It's not, yeah, it's not a positive grade. But this kind of leads to a second thing, which is part of this conjecture implicitly is that this thing might not be an affine variety. I mean, as I said, it's kind of a derived stack. So one needs to make sense. So need to make sense of what it means to be DG cluster. So sense of the notion of derived cluster or cluster DG algebra in some sense. So that's not something that exists in the literature. And just to give you an example, like if you just think about Morse complex sequences, if you think about the positive braids, the Morse complex sequences are such that you have the degree 0 potential 0 and then potential 1. So you just have degree 0 and degree 1 people, and there's one Morse differential, like that big matrix. And I can tell you more theoretically, purely intrinsically, how to name the cluster variables from that. But now in a general front, as you sweep left to right, you're going to have things in potential 0, 1, 2, 3, 4, 5. Now you have tons of matrices. So you're not dealing with like one braid matrix every time you're dealing now with a complex where you have braid matrices like all the way. So now what is the right way to extract the variables out of these kind of complexes whose differentials have to do with the braid matrices? So that's kind of the TG version of that, how we do that, but now with complexes. And in part 2, there's the extra challenge of independent of having or not solved this DG business. You could just say, well, let this be an algebra, but what is the meaning of a non-commutative cluster structure? And that's something that a number of people have been thinking about, including myself. But this kind of started with work of Redach and Bernstein out of Oregon, and then Sasha Goncharov and Maxim Kontsevich also kind of have written some papers about it. And we've done something about it. And it's kind of unclear what the right definition is. Just to give you the key point is, in the mutation formula, if you remember, you multiply the people who are coming in, and then you add the people who are multiplying the people who are coming out. The problem is you don't know an order now. So what I suspect is happening is that one should not try to come up with an idea that doesn't use an order, but rather I think the symplectic geometry maybe is giving you an order of things in some way. It's just naming the disks in a particular cyclic order, and maybe that will allow you to do mutations. Again, this is kind of conjectural, but that would be the basic question would be, what is the cluster mutation formula when you have a non-commutative algebra? We don't know how to choose those products. Nevertheless, the geometry very clearly tells you that Lagrangian surgery happens, and so there should be some kind of universal way to find a formula that goes from the right to the left. So conjecture 1 is kind of hinting at, can we make sense of cluster DG algebras? Conjecture 2 makes sense of non-commutative cluster DG algebras, and then if we make sense of that, then our DGA will be like the prime example of a non-commutative cluster DG algebra, which then, the end of the conjecture is such that both of these classify. Well, both of these should be isomorphic and both classify Lagrangian. But in particular, because already maybe you would expect that it's degree 1 part that's like it's but
I ask a follow-up about the check-on node. So the other check-on node does have a filling, it's just not Maslow's zero.
Yeah.
Right, and so is the issue that it's, like, you could try to do this all like two graded, et cetera.
Yeah.
Um,
No, it's just like, I personally,
We
this
just
is
don't
sort of me not having time. I haven't looked at the filling and tried to find the L compressing disk.
I see.
I mean, I would suspect it's there. It depends on what I need to look at the cluster algebra structure. I would suspect it's not there. Because it's C star, right? You wrote it the other day. You wrote 1 plus xy equals 0.
Well, that's the zero graded one, but
Oh, the 0 graded one. So the ungraded, the Z2.
the two graded one,
Yeah.
it's the same as for the other check-on node.
Yeah, then I would suspect that
It should have a-
our geometric, what I'm trying to do here is always focus on the geometry. And I think the geometric goal there is find a Lagrangian disk that sort of realizes that. Yeah, which, yeah, it's a very good place to start. None of this is meant to be impossible. It's meant to be, it's not proven. It just, we kind of need to get going. And I think, yeah, that's a very good suggestion. Okay, are we okay so far? It doesn't feel like I really went mad or something. Okay, I'm gonna continue a little bit. So, couple more statements. So, I want to tell you about my opinions on immersed fillings, which are different from some people's opinions here, which are also very valid. My dream here was to understand a algebraic phenomena that I witnessed when I was proving all of that. As you might remember from yesterday, one of the key steps was to prove that this space, this variety, the braid variety, was actually covered up to dimension 2 by these open toric charts. And that's a very commutative sounding statement, right? It's a commutative algebra, and gives this like classical scheme, commutative scheme, and you're covering it literally by open charts, maybe okay, up to dimension 2. For knots, it's literally not up to dimension 2, you just get it on the notes. Okay. And if you remember, in that case, it suffices to consider the first Lagrangian filling with the compressing disk and the adjacent ones. And actually, I mean, this might not be obvious at the beginning, but we've proven that those are enough, like in that case. So what I want to suggest is a non-commutative version of that. So let me write this in 3. So these are non-commutative covers. I can do it in shift theory or in DGAs. Maybe I'll do it for DGAs from now. Covers up to DGA of lambda beta. And then once we've understood this case well enough, this is something I actually can prove and everything. But I've been discussing this with Mohammed Abu-Zaid. So this is something should be fine for lambda beta. And then the conjecture is the same story should run for any lambda. And as you will see, I will not use lambda beta except for the fact that there is an compressing system. I can run the whole machinery. So what's the idea here? Well, okay, let me start. So suppose you have your knot lambda in here and you know nothing about it. Let's maybe make it interesting. Something like that. Okay. So now you're going to have fillings, and in particular, you're going to have one filling in here, which is of genus 2. So this is some Lagrangian filling L. Does that make sense? And now this Lagrangian filling L is going to have this L compressing system with the disks D1, D2, D3, and D4. And once you have one of that, you could say, well, I'm going to go and do a Lagrangian surgery. Say you do Lagrangian surgery in the first guy. What are you going to get? You're going to get a surface that kind of looks like that. And this continues like that. And so we're in agreement. This is where D1 has gone now. It's collapsed to a point. So it went to a point. And then you have the rest still sort of like going over. Sorry, this should go to the point. To this point, this one, and this one. Are we okay with that? So that one is obtained by collapsing. Now I can do that for any of the PIs. So here you have a filling. Let's call this filling L1. And this is an immersed filling with a unique point. Okay? A unique immersed point. Now the same story runs for L2, L3, and L4. And the first statement that I want to make is that these augmentation, you can first think as the following process. You first take the DGA of this, which geometrically I would think as the trivial Lagrangian covariism. So this is just the trivial Lagrangian. I know it's kind of silly to think of this as a Lagrangian, but it's kind of what the geometry is telling you to do. So you think of this as the identity Lagrangian covariism. And then the map that goes here is a covariism that will bring this down to the Hopfling, but not any Hopfling. It's the Hopfling that's exactly around that immersed point. So there's a Hopfling kind of around here. And so this will go to something that is equal to the DGA of the Hopfling. So in particular, I'm telling you that a suggestion that I have is that we do think of an immersed filling with one immersed point to be exactly equivalent as the algebraic data from a map from your DGA, a DG map, to the DGA of the Hopfling, like that. And now you can do that 4 times, because in this particular there's 4 things. So you get 4 maps. So here you get an augmentation A at L1, and I want to think of this as an augmentation. I mean, the word augmentation is kind of terrible, but since we've used it, might as well go with it till the end. So I would call any DG map out of your DGA an augmentation. I don't know, you could call it a DG map. I mean, augmentation just doesn't mean anything important. Like, so, you know, classically it means to a field or to a ring, but then it's like augmentations to something else. And then, well, yeah, for instance, I consider this to be an augmentation. It's like the universal augmentation. I mean, the way to make this rigorous, and I will talk about it in maybe 10 minutes, is that I think the right categories to be looking at to understand all of these is the category of modules over the DGA. Maybe I should make a comment about that. Okay, so classically there's aug minus, and then there's aug plus. If you think about aug minus and aug plus, especially aug plus, it's defined really counting certain holomorphic disks and then some multiple copies, and that gives the infinity structure, so on and so forth. But it's a pain in the neck to prove that it's invariant. Maybe if you're Lenny, it's not a pain, but even if you're Lenny, it is a pain. But more fundamentally, if you start to think about Lagrangian covariisms or how it works for higher dimensions, it just becomes completely how on earth do you define augmentation plus like for higher dimensions? You're not going to be able to prove invariance combinatorially. So that category in a way had the feature that it was defined so much using the holomorphic disks that it becomes very hard to generalize and improve invariance and so on. So here's a halfway compromise, which is to say, I use holomorphic disks, and that is in order to name the DGA. Use exactly the holomorphic curve. We want positive punctures, several negative punctures. But then I stop there with the holomorphic theory, and then I just do algebra. Namely, I take perfect modules over the DGA, like the compact objects in the category of modules over the DGA. So from that perspective, all of these are perfectly fine modules over the DGA. And what is the universal module over the DGA itself? Because an algebra always has a representation, a module, which is multiply on itself, like the regular one. So it might sound ridiculous, but my claim is any Legendrian has an augmentation in the sense that any DG algebra coming from a Legendrian has an element in its category of modules starting with itself. And an interesting question is, can you go to other people? Do you have modules kind of beyond that? Okay, so these are modules that I think of them as going down to the DGA of the Hopfling. When I say these are modules, is you take this algebra and you put in the module structure given by this map. That's right. And so now you can start to do a lot of like funny stuff. For instance, you can think of this as a module, pull it back, and then push it forward and try to understand what this is doing. And you can kind of make sense of that. It's like some kind of 4 theoretic intersection between this Lagrangian filling and this one, but it's going to have coefficients and change of the base loop space for this one. So there's like modifications on things that are not in the literature, but Mohammed did that in some cases in the closed case. So you have these 4 maps, and now each of them, because of Lagrangian disk surgery, maps down. You can fill a Hopfling in 2 ways. So each of them maps down to here. Is that Roman?
Should we expect it to be Calabi-Yau category of this perfect category of perfect modules?
Relative cost.
Yeah.
Like relative Calabi-Yau. So it's going to be a category. So if you take the DGA with coefficients and change in the base loop space, there's going to be a map which just takes the coefficients. So that inclusion of the coefficient to the DGA, when you take modules over algorithm flips, that should be a relative Calabi-Yau factor. Yeah. Yeah, there's like 3 groups of people working the first theoretic approach to relative Calabi-Yau structures, and I don't exactly know who's proving what, but the hope is in the next few years, there's going to be a statement exactly saying that. Okay, so here comes the kicker. And this is something you can see very beautifully in the case of lambda beta. This is a pullback diagram. So interpreted geometrically, i.e. the DGA of lambda beta is covered, understood as a non-commutative covered, is openly covered by the DGAs of Li, where Li is the immerse filling given by taking the ith disk in the L compressing system and chopping it. Okay, so I initially was calling these things a generating criterion in the sense that that's kind of saying these people, these 4 people generate, and it is saying that, but it's kind of saying something slightly stronger and also from a perspective that actually is much more helpful. So if you're not used to pullback diagrams and stuff, like I understand, but it's, I shouldn't say pullback. Limit. So limit that. Pullback, if there were exactly 2 maps, you would call that a pullback. In general, it's like that. So the claim is that this DGA is a homotopy limit of all these people with respect to that. So think about it this way. What you're doing is you're taking this torus chart. So sorry, you're taking these charts in here, which I'll talk about in a second. So each of these charts, and then you're gluing them along here. And the claim is these 4 charts glued along this one, they cover your DGA. Yeah. So again, my suggestion is let's venture into the world of what the geometry tells you. And the geometry tells you this non-commutative thing makes sense. Yeah.
So you only need the one L there, you don't need its mutants?
It's what?
You don't have to mutate, you just have.
That's particular about this. It's like and it's yeah, exactly. Yeah, I mean this I don't know, I really like this theorem. I mean, like this is saying you have one filling, and now out of these you can exactly go to the immersed ones over there, and then just by using those ones, you're gonna get any other filling as long as you glue them along this relation. One way to think about it is this guy knows this guy by doing smoothing of his Polterovich surgery, and it also knows the next guy. So you can think of this diagram as this guy and the adjacent ones. But for instance, I never needed the extra 2 away or 4 away. So this is a non-commutative analog of the fact that the initial torus union the adjacent ones cover. But it's kind of even more subtle than that because it's saying you do not need to talk about kind of the extra ones, you're just literally gluing these things. And I think something like it took me a while to understand is that sort of the literature in our conversations, we focus a lot on embedded fillings. And I was trying to glue embedded fillings. I was trying to say these fillings generate. I didn't have a good language for that. And the right thing to do, I mean, I don't know the right thing to do, but the thing that works out is you think about the immersed one, and then you're gluing immersed fillings along an embedded one, and that actually just proves it. So let me give you a sort of short proof in some easy cases. Say that you got from here to here. Well, how do you get from here to here? There is this guy, this variable over here. That is exactly what? Well, if you think about it, what is happening, so now you listen to Lenny, lecture 2, this EHK map, you can think that you've kind of opened a crossing. So what this is doing is localizing along a rep chord. Well, want to guess what rep chord it is? It is the one that gives you the cluster variable associated to this Lagrangian disk. So this is actually simply a non-commutative derived localization of this DGA along that cluster algebra, the cluster variable. So this is a localization along one cluster variable, this localization along another cluster variable, localization along one, localization on another one. So now what happens when you localize a ring in many different ways in an independent set? And then how do you go down to here? Here is the place where you've localized everybody. So if you take the limit of localize everybody and then a bunch of sets, the limit of that diagram is going to be the intersections, but there's no intersections between these cluster variables. So you would get the original ring. Expressed now as a localization, and the localizations are mapping geometrically to these fillings. I mean, no, it's might be a little bit, I really think there's juice there, okay? So let me do an example that I find important to comment on. So the hot link. So why is this example important? Because in this case, you have a unique filling, so you would just pinch the guy. So the statement would be that the DGA of the hot link, like this guy, it kind of maps to here. And now, I mean, you can go down if you want to this. You can add the extra, the smoothing, your favorite smoothing here. But the limit of this diagram is just going to be the DGA itself. So in particular, what I'm saying is the DGA of this immersed filling is isomorphic to the DGA of the hot link. And this leads to a point that, again, I think we should sort of, I would encourage you to open the mind to the idea that what I said was wrong in the following sense. So when we were doing the hot link, we had this picture where there was this place where we had one filling was thought of as being this one point, another filling was thought of as being this point, remember? And then I said, and this is the thing, I mean, I intentionally said it, but like this is the thing I suggested you say, well, he was right in some sense, but that's not the right way to look at it. There was this guy in here, right? Now, is it correct that there is a sheave that gives that immersed filling? Yes, that is correct. And it's a sheave where? It's a sheave on the union of two planes that intersect at a point. Now, what was this chart geometrically? Remember, the one for an embedded filling. This chart geometrically was local systems on the Lagrangian filling, which was a cylinder, right? So here you could say, and this is a way to convince somebody, but it's I think not the right way, which is to say, well, here the Lagrangian filling looks like this. So now the question is, given these two disks, D1, D2, well, what I should be giving myself as a chart, the chart that it induces, is local systems on D1 union D2. Okay, missing a lot of one. And now it's when you're lazy about these and say, well, D1 is contractible, D2 is contractible, this is clearly contractible space. There are no local systems, there's no interesting change in the base loop space or anything. So this should just give you a point. And that's exactly why Roger was saying this is the point for the immersion. All right, that's fine. I think the correct answer is not this one. I think the correct answer is that we should all, like one of us, whoever wants to come up with, we should come up with the right definition of what this means. What does it mean to have a local system when you have an immersed point? And I'll tell you what the answer is, or what I think the answer is. The answer is the local system on this should be understood as, well, I mean, the right answer is it should be just understood as the global sections of the Kashiwara-Shapiro stack on this skeleton. Just that's the right answer. Now, how do you compute it in here? You can compute it, for instance, as sheaves on R2, which are stratified with respect to this point, which gives you the other one. This is classically known as perverse sheaves. Another way to think about it is, why does this guy know absolutely everybody? You could think as follows. You could think, well, what's really happening here is I have the trivial local system, and the trivial local system in this picture gives me this point. But I have another kind of sheaf, which is not a local system, it's a sheaf, but it's as locally constant as it gets in that it is a local system away from the singularity. So if I remove this point, I can have a sheaf on this plane minus a point, and that's a monodromy, and I have another one coming from here, and that is another monodromy in here. So you see, you could say a local system on the singular space, remove the point, and consider a local system over there. How do they extend over a point? You say, well, I give up the idea of being a local system by I let it be a local system away from the singular point, and when it extends, we extend with 0 here, and it's a sheaf. Now, what do we see now? We see the local system that is completely trivial, orange guy, and the local system which is saying C star choices in here and C star choices in there, and that exactly sees this C star and the other C star. So from this viewpoint, local systems, properly understood in a singular space, gives you the entire space. And that's why then this is a nice one. So in my view, the immersed filling of the Hofling gives you the entire augmentation variety. Is that clear?
So, but in this case, this can be seen from the Lagrangian V perspective, right? Since like this immersed feeling is
Well-
just this immersed legend, and you consider shapes supporting this immersed legend
Yes.
as a whole.
But it's always the question is, what is this conceptual? Like, what are you, yeah, okay, so, okay, what he's saying, which makes perfect sense, is to say, look, one feeling is this one, another feeling is this one.
Uh-huh.
So you could say, well, the feeling in between is this one,
Uh-huh.
and now you just say, well, there's no constraint in here, so it's just 4 flags. Oh, that's exactly the same condition as the
Yeah.
augmentation variety, so that's it. But the question is, what is this flag moduli seen as something about sheaves on the Lagrangian?
It is, it's you can tell lambda to be a single legend, you can still define shapes with supporting this single.
I agree, but that's, I mean, we agree. I mean, if you're saying what I'm saying is true, yeah, I agree. So this- No, but I mean, you can do that in this example and everything, but what I'm saying is, we want a more, I don't know, I want a more conceptual understanding of what should I be naming here,
Yeah,
right?
yeah,
Even if
sure.
it's not coming from a weave, even if it's not coming from something. And I agree that here you could say, what are the sheaves that are singularly supported on this singular Legendrian?
Mhm.
But then you would have to take the microvocal functor,
Mhm.
and now the microvocal functor goes to the Kashiwara-Shapiro stack, the
Yes.
global sections,
Uh-huh.
and now you want to compute global sections of that. And that's exactly what I'm saying. Global sections of that is the right answer to this.
Yeah.
And I'm computing it for you directly in this particular case.
Yeah.
Yeah.
It's
We agree.
very
I'm just
concrete, yeah.
computing, like, I'm justifying that this is the conceptual right answer and then computing it directly to explain why it gives the two charts and the plot.
But I thought by definition, this same is the legend embedded in the covariant bundle, so the global sector of Kashiwara-Shapiro stack is the category of shapes supported in this legend here.
Like, we agree.
Oh, yeah, sorry,
Like,
yeah.
I don't know what else to
Yeah,
say.
yeah.
We
Yeah, yeah,
agree,
sure.
but there's a difference between saying, oh yeah, this is true, I move on, versus saying
Yeah,
this is true, now I want to understand it in
Oh,
a
sure,
way
sure.
that I can state in complete generality
Yeah.
and punctorially, and that I can justify this picture, and I can justify this item. I'm just like looking at the same thing from many viewpoints and explaining to you
yeah.
they all match. I agree. Very beautiful comment of yours. This also can be seen from the week.
Yeah.
I agree. Yeah. Okay, so this is where we are, and my sort of conjecture, I'm not gonna write, but the version of the conjecture C3 is I would expect this kind of thing as a general principle for Legend. So when you look at the DGA, I would suggest that maybe we try to look for immersed fillings already with just one immersed point, such that the DGA can be expressed as a limit over the augmentations given by these people. And that is the non-commutative DG way of talking about these guys provide charts that cover this DGA. Does that make sense? We're technically doing non-commutative DG algebras, but we're doing it from the lens of geometric spaces. And so you can certainly go to a conference on algebra and say, I have this kind of DGA, and this is a limit diagram, commutability, and I'm done. But like, we're doing it motivated by the geometry. And so it'd be nice to really become very fluent in this language and conversely, like, understand how that impacts geometry. Eric.
So in your theorem here, can you like actually produce like a Weinstein skeleton, which for this thing, which is filling with disks, or is that not your, or is that your conjecture?
So for lambda betas, we can, right?
Okay.
In general, I don't know. Yeah. So in general, it would be like sort of, this whole thing is really about building L compressing systems in general. It's like, if you have the L compressing system, you try to do that. And again, like, this works in any Weinstein manifold, is that you just need a relative Lagrangian skeleton.
Mhm.
Right, so for instance, if you take CP2 and you take the complement of a smooth conic, a Lagrangian skeleton is like the central torus and 3 disks attached to it. So that the whole thing should still run, like, we can still talk about kind of that DGA and everything. Okay,
And this experiments with on the hub.
well, we've been chatting about this for a few months, and I don't know, like I proved it from the DGA perspective, he proved it from the Fukaya category perspective, and
But this is sort of, this,
for lambda beta, I'm sure this can be made sense precisely, and I hope somewhere next year, like, in some form, it will be made very precise for lambda beta. But I know also it will take a while to sort of understand that viewpoint, and so I'm taking the opportunity here to explain this version of non-commutative open covers, because I find it very, very useful. And in particular, it justifies something which is, Liz has been studying immersed fillings for a very long time. I really think they're central to the picture. And in particular, in this sense, they do generate, even just like fillings with one immersed point. So we should embrace immersed fillings. They're this helpful. Now, so last conjecture, and this one kind of has popped up in some form or another. I don't know how to make this one precise, but it's the last one, so you can only kick me out and. Anyway, so, you know, Weinstein's creed, so Glenn was telling us that Weinstein gave one of his CVMS back in the day, and Weinstein kind of became famous for his creed of everything is a Lagrangian, you know, the example of the graph of simple isomorphism is a Lagrangian, otherwise a Lagrangian correspondence. So I kind of want to say C4, everything is a Lagrangian, but just to keep ourselves a bit more open-minded, I wanna really push the idea that everything is geometric. And by geometric, I mean, we really should be thinking that whenever the algebra is saying something to us, there is a Lagrangian filling in some capacity inducing that. And I think Dan and Yufan's paper is a very good instance of that. It's like any augmentation can be realized from a Lagrangian filling, which is immersed in an obstructed. In general, as I mean, this is kind of what I was asking before. For example, so if you have lambda plus and it's coordinate, so this is a of lambda plus going down to a of lambda minus is a digimap, then there exists a covariism, there exists Lagrangian covariism. And this is in all dimensions. I don't, you know, it could be made for nodes, but obviously any kind of thing, there's the Lagrangian covariism. Unobstructed, I'm not saying it's embedded, maybe it's immersed, but as long as it's unobstructed, as long as it induces it, then it's Lagrangian covariism L from lambda minus to lambda plus, which realizes it. That's one example of this kind of very childlike philosophy, and I agree, it's very childish. It's like, oh, you haven't been out in the world, you just think everything's gonna be this nice. I don't know. Yeah, I still think that way. I've been out in the world for a bit. I still feel this way. So this is one example. Another thing that I would encourage people is we were saying things sometimes like, oh, this node does not have a Lagrangian filling or blah blah blah. Maybe we should change our language and really talk about obstructed and unobstructed fillings instead of immersed or embedded, just obstructed or unobstructed. And then my hope would be anything the ruling polynomial or anything that the augmentation operator tells you it exists, it comes from an obstructed fill. Does that make sense? So this is, I mean, obviously done, and you can't prove that in dimension in which you have a node, but in all dimensions, say example number 2, in all dimensions, augmentations are geometric. So augmentations come from an obstructed Lagrangian fillings. And I mean, I know I can keep giving you examples of these things, but that is sort of the spirit of it. And sort of also in the spirit of this, kind of Sheaf or core theory sees everything. Is a suggestion. This might be awfully wrong, but why not? So so this is the covariism theorem. In some vague form. So if you just look at sort of the history of geometric topology, particularly smooth topology, there's often not that many theorems, there's like 4 or 5 theorems that really get being used constantly, and certainly for high dimensional topology, the turning point was the edge covariism theorem of Smale. Now, I don't know of anything even close to the Lagrangian version of that. It sounds very challenging. As I was telling the company the other day, like, one reason I got initially discouraged when I was thinking about these things is they prove this theorem, for instance, it says if S3 has a contact form that has more than, say, 3 rep orbits, then it has to have infinitely many. And in SN, if you have like more than n orbits, then you're toast. You can see this more theoretically as saying it is not possible to create a canceling pair for the Morse action functional on the loop space in a way that you stay within there. It's certainly fine to create a canceling pair. You're just getting out of the category of functionals that are of the form integral of alpha. I mean, there's a functional like that, it's just not of the form integral. That's essentially what the theorem is saying. Like within that, you can interpret it that way, right? And I just like was really bummed down, like there's no H cobordism that says if I have two contact manifolds and a symplectic cobordism between them is if CH of these and CH of these, if the map from this CH to this CH is such that it's an isomorphism, then it's like a trivial symplectic thing. But how could you go about proving that? You would literally say, well, I'm going to try to cancel pairs of rep orbits, but if you cannot create them, you cannot cancel them, like kind of situation. I mean, maybe you can in some sense, but it's not something I understand. But for the Lagrangian setting, because it comes from generating functions specifically, I think there's like a vast generalization of Cerf's paper and sort of the H cobordism. So Cerf's paper, which is about the way he wrote it, is about trying to understand the space of Morse functions from no critical points to no critical points, and you think of the Cerf diagram in the middle as the front of the Legendrian. If you read his paper, which I strongly recommend, it is kind of long, but it's really well written. What he's doing is essentially he's building a Lagrangian filling frame. Like he didn't say it that way, but that's his process. And he does so in two steps. First, he does a bunch of class moves that are allowed. He doesn't call them that way, but that's really what it is from the modern viewpoint. And then you guess what he's down to? Then he's down to something of lambda beta. There's literally this beta diagram in the Cerf paper. And then he says, well, now I need to argue that I can like kind of keep doing that. And that is a one parametric version of the S cobordism theorem, well, the H cobordism theorem, because he was using by one. So I would really say maybe let's embrace Cerf's paper as a really starting point that H cobordisms might have a lot to do with Lagrangian fillings and Lagrangian cobordisms, so on and so forth. So I'll just throw this out there. So suppose that L goes from lambda minus to lambda plus. So and now maybe let's just put some hypotheses so it's not too bad. So the dimension of L, so say this is dimension of n plus 1, this dimension n, with n large enough. So you can do windy type tricks. And L is smoothly trivial. So L is smoothly trivial. If you wish, you could say it's like an H cobordism or an S cobordism. So there's no, then smoothly, I mean formally trivial. Smoothly trivial. Then L is Lagrangian trivial. L consequence is Hamiltonian isotopic. I mean, lambda plus has to be lambda minus smoothly because of that. It's Hamiltonian isotopic with 7. And in particular, it would imply the typical consequence of the H cobordism that these two guys are Lagrangian. So how would you go about proving something like that? I mean, ideally, what you could think about is, well, the H cobordism is using that the homology of these injects in an isomorphic way the homology of the total space and sent from the other side. Now, we don't have both symmetries in the symplectic world, but you can still think about the map from this DGA to this DGA to be an isomorphism. And shift theoretically, you could take the Legendrian lift of that, and there's the restriction map this way and the restriction map this way, but this one is fully faithful. So you can still talk about both sides, the way they talk to each other. And then the first step in Smale's proof of the H cobordism is a geometric cancellation lemma that says if I have two critical points, there's nobody in between that are critical points, and they exactly are connected by one trajectory, then I can go and cancel them. So I think I asked Lenny the other day, but I currently do not know any obstruction to the following version, the Lagrangian version of that, which is suppose you have two rep chords here and here. They're connected by a unique cylinder. There's no rep chord with action in between these two cases. Then you can actually cancel both of them. There's an easier version of that, which is just think about closed Lagrangians, like Weinstein manifold, which is suppose you have two Lagrangians which have two immersed points. These are elements in their Floer homology, in their homology of L and L prime. And suppose again, there's nobody with action in between. And now you have an holomorphic disk in between. Question, can you use that holomorphic disk to do some kind of Lagrangian windy trick so as to separate those two immersed points? So that would be maybe where one could start the Lagrangian analog of the first step of Smale's proof. And then the second one, which is kind of the more challenging involving algebra, is the one that tells you algebra and plot geometry. Namely, if you have a differential that has this immersed point, this on between the two Lagrangians, and then many people, that there's a way to rearrange things so you end up exactly in the position of 1 and 1. And then you would write the geometric cancellation. I don't know. I think it's worth exploring. You're not in any way forced to do it. You can just let me think about this, and I'll report in a few years. But I think really we are working on something that beautifully connects to many things, and it's important to push for geometry, to push for actually finding Lagrangian fillings, trying to take geometric constructions and seeing where they fail and where they succeed in our world. And I know it's beautiful to do shift theory, it's beautiful to do floor theory, it's beautiful to do like algebraic invariance and all, but I kind of would encourage everybody to also keep rooted in the geometry of things and trying to make things as geometric as possible. And it will be interesting when we fail to do so, and then maybe we'll learn something from it. But that's sort of one of the messages I wanted to convey. And with that, I'm finishing the lecture series. Thanks.
So before we take a break, I would like to say we did forget to thank one person. So I'd like to thank Roger for agreeing to give these lectures and write this really detailed set of notes. I think this is going to be super valuable for people for decades to come trying to learn this material. So thanks a lot.